Yo, what's up, everyone? Welcome to Equilibrium Part 5. Today we're going to be talking about buffers, and eventually all of this is going to lead to something known as the Henderson-Hasselbalch equation. So by the end of this, hopefully you'll get an intuitive understanding for how and why the equation works. So let's start with a definition of a buffer. A buffer is a solution in which the pH resists a change when strong acids or bases are added. And a buffer is necessary for a lot of biological mechanisms. And a lot of biological mechanisms, like your body and like the ocean, you need a certain pH to exist. In your body, if your body goes over like a safe pH, your enzymes will stop working. They change their shape, and then your enzymes no longer work, and then you'll die. So you really want something that can resist a change in pH, and that something is a buffer. And so, what does it mean for something to resist a change in pH? Well, pH is just a measure of how many hydronium ions are in your concentration, are in your solution. So you could have a lot of acids that come into your solution that will really increase the hydronium concentration, or you could have a lot of bases that will produce a lot of hydroxide ions, which will also change the pH a lot. So you want something that can resist changes to concentration in hydronium and in hydroxide. And so for that, we need two different things. You can have a buffer with a weak acid and the salt of a conjugate base, or you could have a buffer with a weak base with the salt of a conjugate acid. So one of the things that you can have is a weak acid and a salt with a conjugate base. So you always want an acid and a base. In this case, we have our acid, which is a weak acid, is nitrous acid, and then you have the salt with a conjugate base. In this case, the salt that we have is sodium nitrite, and since it's a salt, what's going to happen is that whenever it goes into a solution, it's going to dissociate. Oh, sorry, that should not be there. It's going to dissociate into your sodium ions and then your nitrite ions. And this nitrite ion is slightly basic, and so that's where the base is coming in from. You want a weak acid plus a salt with the conjugate base, or you could have a weak base with the salt of a conjugate acid, which we will look at later. So let's look at this example. We have nitrous acid and then sodium nitrite. Our buffer needs to have systems in order to mitigate changes in hydronium concentration and hydroxide concentration. So let's say you add a strong acid to your buffer. Let's say you have a solution. Let me do this in a different color. Let's say you have a solution, and within that solution, you have, that is not straight. Let me erase that. You have a solution, and then you add a bunch of strong acid to it. So you have a solution, and then you have a bunch of your weak acids there. That can be the level. You have a bunch of your acids there, nitrous acid, and you have your conjugate base too. So that's going to dissociate into sodium ions and then your nitrite ions. Now your solution here needs to have ways in order to get rid of extra hydronium ions. So if I add a strong acid like hydrochloric acid is a strong acid because it dissociates completely. So it's going to react with water to produce hydronium and your chloride ion. Now your system needs a way to get rid of that hydronium. So how does it do that? Well, the hydronium reacts with the nitrite ion from the conjugate base, or from the salt with the conjugate base, to produce your weak acid again. You create your nitrous acid again, and then you also create some water, which has no impact. And so that's how your buffer gets rid of an acid. Now, you could also have a strong base. In this case, we have sodium hydroxide, and it's a strong base because it dissociates completely into your hydroxide ions and your sodium ions. And in this case, the hydroxide ions, in order to get rid of your hydroxide ions, the hydroxide reacts with the weak acid itself to produce that nitrite ion again, and then your water. So essentially, it's kind of like a cycle. Whenever you have a strong acid, the hydronium ion reacts with the conjugate base in order to get the weak acid again. And then in a strong base, your hydroxide ion reacts with the acid, your weak acid, to create the conjugate base again. So you can see why we need both a weak acid and the salt of a conjugate base in order to have a buffer. You could also have the other side of the story, which is a weak base with the conjugate acid. And so in this case, we have our ammonia and then our ammonium chloride. And so let's say you add a strong acid. In this case, again, it's hydrochloric acid. It dissociates completely into your hydronium ions, and you need a way to get rid of the hydronium ions. Now, the hydronium ion is going to react with the weak base, the ammonia, to produce your ammonium ion and some water. And then the opposite works for a strong base. So a strong base like sodium hydroxide, you have an influx of your hydroxide ions, and so your ammonium ion reacts with the hydroxide to produce your weak base again. So again, it's always a cycle. It's back and forth. Whenever you have a weak acid coming in, it reacts with the base to produce the acid again. And then whenever you have a base, it reacts with the acid to produce the base. And that's how these buffers keep going back and forth. Now, let's calculate the pH of a buffer, because buffers are going to have a certain pH based on what you put inside of them. So let's say we have, what is the pH of a buffer solution that is 0.4 molar nitrous acid and 0.4 molar sodium nitrate. And we're told that the Ka of our acid is 4.27 times 10 to the negative 4. For questions like this, you have to first consider, where are the hydronium ions going to come from? From what is the hydronium ions really going to be produced from? Because that's going to determine the pH of your solution. So the hydronium ions are going to come from the nitrous acid. So we have HNO2, and that's going to react with water to produce your hydronium ions. It's going to be in equilibrium with your hydronium ions, and then it's also going to produce that nitrite ion. And we're told that the Ka of this reaction is 4.27 times 10 to the negative 4th. And what does the Ka mean? Remember, the Ka is just your equilibrium expression. So the Ka in this case would be the concentration of your products, so the hydronium ions and then the nitrite ions, the product of them, over the concentration of your nitrous acid. And so that's what your Ka is. Now, what we really want is the concentration of the hydroxide. Remember, all of this is to get the pH, and the pH is the negative log of your hydronium concentration. So we can rearrange this expression to isolate for your hydronium. Now, that's going to come out to Ka times the concentration of your nitrous acid, NO2, over your nitrite ion. That's just like an algebraic manipulation of your equilibrium expression. And so now you need to figure out, you know what your Ka is, you need to figure out what is your concentration of your acid, and then the concentration of your conjugate base here. Now, if you look at this reaction here, you'll notice that the acid is going to dissociate into hydronium and nitrite. But the thing is, this is a weak acid. The whole point of a buffer is that it's with a weak acid or a weak base, but in this case we have a weak acid, so it's not going to dissociate a lot into our products here. So instead, in order to find our concentrations, we have to look at the initial concentrations that are going to be in this solution. So if you look at your initial problem statement, you're told that the initial concentration of your acid is 0.4 molar, and the initial concentration of your salt here is also 0.4 molar. Now, just because we know the concentration of our salt doesn't necessarily mean we know the concentration of our conjugate base right away, but in this case, our sodium nitrite is going to dissociate into sodium and nitrite in a 1-to-1 ratio. So that means whatever concentration of our acid that we have is also going to be the concentration of our conjugate base. So we know the concentration of your acid, and we also know the concentration of our base here. And technically, the concentration of our acid should be lower than what we put it as, because again, some of it is going to dissociate into hydronium and the nitrite ion. But it's so small. The fact that it's a weak acid means the dissociation is so small that it's basically negligible. So let's write this all out. We have Ka, this is the concentration of the hydronium, is equal to Ka times the concentration of our acid, which we know is 0.4 molar, 0.4 molar, over the concentration of our nitrite, which we know is 0.4 molar, since our acid and our conjugate base are in a 1-to-1 ratio. And so our Ka is 4.27 times 10 to the minus 4 times 0.4 over 0.4, and that is going to come out to just 4.27 times 10 to the negative 4th. These just cancel out because they're the same. And remember, what did we just solve for here? We solved for the concentration of our hydronium. So the concentration of our hydronium ion is 4.27 times 10 to the negative 4th. But we want the pH, and the pH is the negative log of your hydronium concentration. So if we do the negative log of that number, 4.27 times 10 to the minus 4th, that's going to get you your pH. And let me do that really quickly. 4.27 times 10 to the negative 4th. Your pH comes out to about 3.37. And so that's the pH of your buffer solution here. And that is the answer. Now, you might notice something nice. The fact that our acid and our salt had the same concentrations meant that we could cancel both of these out. But it's not always going to be like that. Sometimes the concentrations are different and you have to go through this calculation to figure it out. But whenever you have a buffer in which the acid and the salts are of equal concentrations, the pH of your solution is just going to be the pKa of the acid. The pKa is the negative log of your Ka, and if you notice, that's exactly what we did here to get our pH. So whenever you have a situation like this where your concentrations of the acid and the concentration of your salts are the same, your pH is just equal to the pKa. And that's how you can create really nice buffers by just referencing a pKa value. You'll sometimes want a buffer with a certain pH, and so that's how you can design buffers in order to have that certain pH. Now let's do a different problem. In this case, let's say we dissolve 2.5 grams of hydrochloric acid in a 500 ml solution of 0.4 molar nitrous acid and 0.4 molar sodium nitrite. So we have the same buffer here, but in this case, we're adding our strong acid. We're adding a certain 2.5 grams of our strong acid. And we're asked to calculate the pH of the resulting solution and the change in pH. And we're told to assume that the volume of the solution remains constant. So the whole point of a buffer is the fact that our pH should not change that much. Even though we're adding a strong acid, which should technically inflate the concentration of our hydronium, the pH should not be different from the pH, or should not be very different from the pH that we calculated before. So the pH that we calculated before was 3.37, so let's keep that in mind. And so how do we find out the change in pH? Well, again, it helps to write out the reaction. And the reaction is that, or the initial reaction is the fact that our acid reacts with water to produce your hydronium ions and your nitrite ions. Now, whenever we add hydrochloric acid to this, the hydrochloric acid is going to react with water to produce your hydronium ions and your chloride ions. Now, the chlorides have no effect on the pH. It's just really going to be the hydronium that we have to look at. And so let's first calculate how many moles of hydronium are going to be produced. We have 2.5 grams of hydrochloric acid, 2.5 grams. And so how many moles is that? Well, 2.5 divided by the molar mass of hydrochloric acid, which is 36.45. That's about 0.069 moles. And since we have the moles, we can also calculate the concentration. So we know that this is in a 500 milliliter solution. So our concentration of your hydronium is going to be 0.137 molar. So this is how much hydronium ions is going to be added to the solution from the hydrochloric acid. Now, just because it's added doesn't mean it's actually going to go into our final pH, because another reaction is going to take place. Now, the hydrochloric acid is going to react with our nitrite to produce your acid again, HNO2, and your chloride ions. So essentially, although we have a bunch of our hydronium ions that are being put into the solution, we have a way to get rid of them. And in this case, you can write the net ionic equation, so you can just say that the hydronium reacts with the nitrite ion to produce your acid, HNO2, and just some water, instead of that equation up there, if it helps you think of it that way. So essentially, a lot of your hydronium is going to react with the nitrite to produce your acid again and some water. So if we write our Ka expression here, or our concentration of hydronium from our Ka, because that's really where all our pH is going to be coming from for this acid. So we have from our old thing there, let me do it in that color. So let's say your hydronium is going to be equal to Ka times the concentration of your acid, HNO2, over the concentration of your nitrite, NO2 minus. Now, from this equation here, you know that the hydronium is going to react with the nitrite to produce your acid. So that means that the concentration of your nitrite is going down, and the concentration of your acid is going to go up. And how much is it going to go up? Well, it has to react with all this excess hydronium. So the concentration of your ammonia is going to go down 0.137 molar, and the concentration of your acid is going to go up 0.137 molar. And so we can write that again. We know that our Ka is 4.27 times 10 to the minus 4. You know your acid concentration is going up 0.137 molar. So if we add that to our initial 0.4 molar, that is 0.537 molar. And that's over the concentration of your nitrite, which you know goes down 0.137 molar. So 0.4 minus 0.137 is 0.263 molar. And if you do add the calculation on this, so 4.27 times 10 to the minus 4 times 0.537 divided by 0.263, your new concentration of hydronium is going to be 8.72 times 10 to the minus 4. And so that is your new concentration of hydronium ions. And if you do the negative log of that, if you do the negative log of your concentration, you get the pH times 10 to the minus 4. And you get that your pH is 3.06. So your pH is now 3.06, and your change in pH, remember it was initially 3.37, so now the change is 0.31. And so you can see how the buffer, because of our buffer here, our pH only decreases a little bit. And it makes sense, oh yeah, whatever, 0.05. Our pH doesn't really decrease that much, and that's because of the buffer. And another thing is that our new pH is less than our initial pH because we added a strong acid to this. We added hydrochloric acid, which should make the make the pH lower, but it shouldn't make the pH lower by very much, and that's really important. All right, now let's say you have a buffer with the acid HA and the base A minus. We're essentially, the point of all of this entire math that we're about to do is to generalize what we did for here for any other acid that we can, or any other buffer that we want to deal with. So let's say you have a buffer with the acid HA and the base A minus. the equilibrium expression here would be this. So your acid reacts with your water to produce that base, and then your hydronium concentration. Now your Ka is just going to be that. That should be a plus. Sorry, I just noticed. That should be a plus. And if you rearrange for your concentration of hydronium, you get that. So your hydronium for any buffer with acid HA and A minus, your hydronium concentration is just your Ka times the concentration of your acid over the concentration of your base. And the reason I say acid and a base is because you could have a buffer with a weak acid plus the conjugate base, or you could have a weak base with the conjugate acid. And so you kind of want to just generalize it. You just want to say base and acid instead of having two separate formulas for the two different types of buffers. So in the weak acid plus conjugate base scenario, the acid would just be the weak acid, and then the base would just be the conjugate base. And then on the other hand, in the weak base plus conjugate acid combination, your base would just be the weak base, and your acid would be the conjugate acid. So your hydronium concentration is just your Ka times the concentration of your acid over the concentration of your base. Now, we want the negative log of our concentration because the negative log of our concentration of hydronium is the pH. So we can take the negative log of both sides, and you do a little simplification. The negative log of Ka is pKa, and then you can do a little manipulation to flip the fraction here to get a positive log. And so your pH comes out to the pKa plus the log of your base over the acid. And this is known as the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation is really helpful for finding out the pH of a buffer without having to do a lot of calculations around it. And remember, it's the pH is equal to pKa plus the log of your base over your acid. Remember, use pKa. Sometimes you'll be given a base, but the base has an equilibrium value that is Kb, but you want Ka. So you want to find out the Ka of your conjugate acid. So that's your Henderson-Hasselbalch equation. Let's do a little example to see how that works. Let me write the equation again so you don't forget. pH is equal to pKa plus the log of your base over the log of the acid. Alright, so calculate the pH of a solution that results from the addition of 0.04 moles of nitric acid to a buffer made by combining 0.5 liters of 0.380 molar propanoic acid and 0.5 liters of 0.38 molar of sodium propanoate, and assume that the addition of the nitric acid has no effect on the volume. Alright, so let's first calculate our pKa. So the acid that we have is propanoic acid, HC3H5O2. It has a pKa of 1.30 times 10 to the negative fifth. If we want pKa, that's just the negative log of your Ka, which is the negative log of your 1.30 times 10 to the minus fifth. And if you do the negative log of that, 1.3 times 10 to the minus fifth, that is 4.89. So that's your initial pKa. And so we have to find out the concentration of your base and your acid. So we know that you're adding 0.04 moles of nitric acid. And 0.04 moles of nitric acid is, we need to find the concentration of that. Since we're combining 0.5 liters and 0.5 liters, your final volume is 1 liter. So our concentration of your acid, HNO3, is going to be 0.04 molar. So we know that whatever our initial concentration of our base was, the concentration of the buffer is going to have that base be 0.04 less than what it initially was, and then the acid is going to be 0.04 more than it initially was. So if we do out the calculation, the pH is pKa, that's 4.89, plus the log of our initial base concentration, initial minus 0.04, over the initial acid concentration plus 0.04. So what was the initial concentrations of the base and the acid? Well, pH is equal to 4.89 plus, I'll just erase that, plus the log of our initial base concentration. So our initial base was 0.5 liters of 0.38 molar of our sodium propanoate. But the thing is, you're combining 0.5 liters of that with 0.5 liters of your acid. So that's going to make the concentration half of what it initially is. So our initial concentration is 0.308 divided by 2. So 380 divided by 2. So that's 0.19 minus 0.04 over 0.19. The acid initial is also the same since your concentration is just, and your volumes are the same. So the concentration of your acid also gets halved. But in this case, we're adding 0.04 to that. So if you do out the calculation here, that comes out to about 4.70. And so the pH, the final pH, is 4.70 after you've added your nitric acid to this. So you can see, and that is the answer, you can see how your Henderson-Hasselbalch equation makes a lot of the other steps simpler. Now, I wrote out a lot of the steps here just to make it really clear, but you could really jump from like that step to that step to that step. And so you could do this problem in 3 steps, and it'd be really, really simple. And so the Henderson-Hasselbalch equation kind of simplifies everything, and it's helpful to know where it's derived from. Now, the last thing I want to talk about is buffer capacity. Buffers don't always work. You can overload a buffer to the point where it doesn't work anymore. So let's say in a buffer, you're going to have an acid and a base. You could have a weak acid and the conjugate base, or you could have a weak base and the conjugate acid. But regardless, you're going to have an acid, you're going to have a base. Now, let's say you're adding more acid to this system. You're adding strong acid to this buffer system. In order to add the acid, in order for the buffer to work at a good capacity, when you add a strong acid, you need the concentration of the base to be at least 10% of the concentration of your acid. And it goes the other way around too. If you have a strong base, let me do this in green, strong base, you want the concentration of your acid to be at least 10% of the concentration of your base. Now this is at least, so you could have a lot more than that, but you don't really want a lot less than that. And if you do out the calculations for what this means using the Henderson-Hasselbalch equation, a buffer works at plus or minus 1 of its initial pH. So let's say our initial pH was 3.37 as we had before. If the pH of your buffer solution goes below, so less than 2.37, or it goes, that should be less than 2.37, or more than 4.37, this buffer system doesn't really work. If it goes past this point, if it goes past that point, then your buffer is not really able to it's not able to handle both strong acids and strong bases. Now you could have systems where you know that you're going to be adding a lot of strong acid to your buffer, so you could have the initial concentration of your acid be really low and just have a lot of base, and so that buffer would not be able to handle strong bases coming in. But since you want a buffer just to deal with acids coming into your system, you could design a buffer where you have a lot of your base but not a lot of your acid, and that would still work fine. But if you want a buffer in which both strong acids and strong bases are handled well, you want that system to be in plus or minus 1 of its initial pH. And so that's buffer capacity. And that was buffers. I hope this was helpful. I hope you're able to get an intuitive understanding of buffers and why you need a weak acid or a base, and then the conjugate salt with the conjugate base or acid of that in order to have the buffer work. I hope you understand how the Henderson-Hasselbalch equation works. I hope this was helpful. I hope you were able to learn something, and I hope to see you later. Thank you.